Hi everyone. So I'm back with a new topic which is thermal stress. Okay, so temperature change causes the body to expand and contract. The amount of linear deformation is given by the formula. So this stands for a thermal deformation where it is a product of alpha, L, and the change in temperature. The change in temperature is equal to the final temperature minus the initial temperature. Okay, so for the different notation used, no, so we have alpha, the coefficient of linear expansion in a unit of meter per degree Celsius, or any other equivalent unit for your L that stands for the original length in meter. Then, ang atong change in temperature in degrees Celsius, so final temperature, initial temperature. Now, for still, if none is mentioned, then the coefficient of linear expansion is 11.25 times 10 to power negative 6 per degree Celsius. Now, for your coefficient of linear expansion, the unit of length, which is meter per meter, so may not be included because meter per meter is just like a unitless value, no? So, or you can just go directly with per degree Celsius. Okay? Now, how to solve when you encounter thermal stress problems? Okay, you are given guides, no? So, imagine that the structure is relieved from any load. Then, allow the thermal deformation to take place freely. Then, third, you have to reapply the load and take the relationships between the thermal deformation and the axial deformation. So, these are the formulas ng atong nalabyan. Thermal deformation. We also have axial deformation. And this is the formula for thermal stress. Now, so the thermal stress formula may be used directly, but be careful because this formula may be applied only if your supports is unyielding. So, just like this one, to find the thermal stress for homogeneous rod that's mounted between two unyielding supports. No? So, like this. No? So, that formula can be used directly if you like. Okay? So, these are the support and this is unyielding. So, if there's a change in temperature, especially if the temperature is increased from initial to a final temperature, so the tendency of which is to expand the member. Okay, so if there's a support here, so we can just assume an imaginary expansion of your length like this. And this is the change in length, which is the deformation due to temperature. But because of the support, no, so it's prevented from expanding. No? So there is a stress that is developed there because ma-post man imong body because of the support. So, ang ato garong sa increase in temperature will cause compression in the member. So, kung imo ding i-drop sa imong temperature because the body will be shortened, no, and it's prevented from shortening, so dunay force which will pull your body and that will make the body to experience a tensile force or tensile stress. Okay? So, as the formula, now for the stress, no, so it's a product of modulus of elasticity with a coefficient of linear expansion and the change in temperature. So this is per degree Celsius, say, and this is in Celsius, degree Celsius. So the unit for temperature can be removed. So the unit of stress will depend on the modulus of elasticity. So if we have to, we want to have a thermal stress expressed in megapascal, then I have to let my modulus of elasticity be also expressed in terms of megapascal. By the way, this formula may be derived, no? So, just like this. If there is a deformation due to heat, if the deformation due to heat can take place freely, the member will not develop any stress. No? So, if you just allow the member to expand or to contract, no, freely, so there is no stress that is developed. However, if the deformation of the member due to temperature change is restrained, like providing supports on both ends, no, then it creates internal stress, and that internal stress is known as a thermal stress. Okay, so we have figure below. Okay, so this is the same kanina, where by expanding or by increasing the temperature, so it allows the body to expand. Okay, as if the support is not provided and it can extend freely. But since there is a support, so we can just have an imaginary expansion of the body linearly. And this is the linear deformation due to heat or due to temperature. The load or stress is developed since the body is prevented. As I mentioned, when there is kung doon na siya support dire. Now, so it's prevented. Now, since the body is prevented to expand freely, as if the load is reapplied to bring it back to the location of the support, causing an axial deformation. So sa ato ba kung doon na kuno ni siya load dire, kay doon na mo ni siya force ma-develop dire, that force will be exerted on that manner, the purpose of which is to bring back this expanded length of your member into the original location of the support. And by doing, so mo na doon na kay axial deformation, and if there is an axial deformation, it is also associated with stresses. Now, so just like this, so there is a deformation due to temperature, and kining imong force dire mo build up na siya because as if dunay force nga mo build up kay mo post man ni dire. No, so it is prevented from expanding, so there is a force that is developed. So the amount of force needed is the force that is needed to bring this end to the location of the support. And by bringing that to the location of the support, then you have the axial deformation. Now, if you look at the diagram, the axial deformation and the thermal deformation can be equal. Okay, so axial deformation and deformation due to change in temperature are now the same. And by formula, this is PL over A with the modulus of elasticity in the denominator. Well, kine, as defined, this is coefficient of linear expansion, the original length, and the change in temperature. But since we are after 4, defining the stress, then the stress is also recalled being a ratio of P over A. So this can be changed to stress. This is P over A, which can now be stress. Ang imong L and the equation form here will not appear because L is common on both sides of the equation, and that L can be eliminated. So what is left is only stress over E. And this one is alpha with a change in temperature. So defining your stress, so you multiply by E. That is why we come up with the equation for thermal stress, or the formula for thermal stress nga atong napakita a while ago. No? So, we were able to show the derivation, and take note that this formula can only be applied if these supports are unyielding. No? So, okay. So, let us have a problem. Problem number 1. If there's a steel rod having a length of 2.75 meter long, that is secured between two walls. If the load on the rod is 0 at 20 degrees Celsius, then compute the stress when the temperature drops to negative 25 degrees Celsius. Area of the section is given, 1,200 square millimeter. The coefficient of linear expansion is 11.25 mu meter per meter degrees Celsius. So, kine, this is equivalent to 10 to power of negative 6. No? So, just take note. The modulus of elasticity for your steel is 200 gigapascal. Now, you are asked to determine the stress assuming the walls are rigid. So, meaning, the walls are actually, or the support is unyielding. No? So, that means you are free to use the formula we derived a while ago. In letter B, assuming that the walls spring together, so as the total, with a total distance of 0.6 as the temperature drops. So, ang ato karon nga unsa, ang ato karong support is actually not fixed, so it is affected with a change in length. So, there is a yielding, total yielding amon sa 0.6 millimeter. Okay, so let me start with A, Okay, so solution for A, because the walls are rigid walls, so it is a kind of unyielding support, so we can make it. Or you may have the diagram, no? Pwede ka mag-diagram, and you have to show that the deformation due to stress, to load, and the deformation due to temperature are the same. So, if this is the original length, just enough to touch the support, no? And then it is dropped at negative 25 degrees. So, the possibility of that without the support is to have this shortened by this amount. but it is prevented from shortening. So there is an amount of force that is developed as if this is being pulled, no, to elongate. So ganina na shorten siya due to temperature, and the force is needed in order to have this be elongated on the same location as the support. So obviously, the thermal deformation and the axial deformation are actually the same, no? So the same manner when we derive the formula ganina. Pero that derivation of formula may be omitted because we are also provided with the derivation, with the formula we derive that the stress is equal to modulus of elasticity, coefficient of linear expansion, and we have the temperature change. Okay, so 200. Now, I want to express this in terms of megapascal. So, if that is gigapascal, so I may write it in terms of mega. 200 times 10 to power 3 to make it megapascal. Megapascal is 10 to power 6. Gigapascal is 10 to power 9. So, if this is 10 to power 6, na pinahabilin nga 10 to power 3. So, 200 times 10 to power 3 megapascal is good as 200 gigapascal. The coefficient of linear expansion is 11.25. Sa akong ingon dire, that is equivalent to times 10 to power minus 6 per degree Celsius. Just omit the meter per meter. Okay, then we can multiply the change in temperature. The initial temperature is 20 degrees, and this is the final temperature. So, minus 25 minus 20 is a change which is negative 45. Pero as to dimension, we take it na lang as absolute, and this is 45 degrees, no? Because the dimension, the coefficient, the length dire ato man asang gibutang sa as the dimension. Sa ato na lang siya gibutang absolute value. There we have the amount of stress that is developed on the body. 101.25. Assuming that the walls are rigid in B. So, we already have the answer, eh? So, ang atong wall kuno dire is rigid, is not rigid. So, it means it has a certain yielding or it moves because of the load. So, if the body will shorten, so kana there is a tendency for the support to give way, no? So, panalitan ni yield siya by 0.6. So, actually, both supports. But, in order to easily interpret our problem, so I just let one support be fixed, anya ka mo atong i-move, no? Okay, so it is yielding by 0.6. So this is the figure for B. If it yields by 0.6, no? Okay, originally this is your support location, and this is now the final location. Okay? It yields because of the decrease in temperature. So the body is imaginarily ni shortened by this much, and this is the thermal deformation. Now, when it is yielding by 0.6 now, so there is an effort to bring the end dire to the location of the support, which is dili dire but dire ras kotob na lang na. Okay, so that amount of force is intended to bring the tip of the body on this location, and this is the deformation due to the force being exerted, diba? So this is now the axial deformation. Now, looking on the diagram, if I have the thermal deformation here, the thermal deformation is equal to the sum of axial deformation with the yielding of 0.6 mm. So, what would be my equation? Okay, ngini. Thermal is equal to axial deformation, then we are adding the 0.6 mm. So, it means that every term here will be expressed in terms of mm. What is the formula for the thermal deformation? Okay, so we have alpha L and the change in temperature, correct? Then this one, this is stress, correct? So we are after for the stress. So atong ipagawas ang stress, this is supposed to be P over A. So stress for P over A, then L with E. Now you cannot remove your L. Why? Huwag mo si L there. This is just a constant 0.6 now. So we can just substitute the value directly. Okay, so by substitution, so we have 11.25 times 10 to power negative 6 per degree Celsius. Your L, which is originally 2.75 meter as to the value, so imo na siya ibutag mm para the unit of which will also be the same unit in your last term. So the unit for every term will be dependent on the length L. A non-stress, correct? Then L is again 2750 millimeter. Ang E will be made express it in terms of megapascal, so that your stress will also be in megapascal as answer. Okay, so mm will be out, correct? Sa degree Celsius will also be eliminated. The unit left is megapascal, and this is the value for your stress when calculated. What is the value? Okay, so you have the answer of 57.614 megapascal. I just put the steps on how to solve a thermal stress problem because whenever dili ka mo diretso directly with this, so you can just simply follow the steps of solving. And for the stress, pero ganang nga stress formula dili magamit dire because this is only good for the first case. Okay? So the condition of the problem must be analyzed, na especially relationships of the deformation in your diagram. Okay, number 2. There is a steel rod with cross-sectional area of 0.3 square inch that is stretched between two fixed points. In order to reach the other end, so a tensile load of 1,250 pounds at a temperature of 75 degrees Fahrenheit now is applied. Now, if the coefficient of linear expansion is also given, and your E is also given. So it is the value of the stress is needed when the temperature from 75 degrees it is being dropped to 0 degrees. Okay, so here is the figure. Now, if this is the location of the end, now that is 75 degrees Fahrenheit, by pulling this member padong diha by applying a force, so this body is already subjected into an axial stress, correct? Now, the initial temperature is 75 degrees when the tip of the bar or rod is at this location. But when the temperature is dropped to 0 degrees, okay? So this is also accompanied with the thermal deformation. So there are two deformation taking place. The deformation due to temperature and the deformation due to axial stress or due to the load direct. Okay, pangutana, what is the stress to form these two deformations? The deformation in your diagram is the sum of the deformation of due to change in temperature and deformation due to the axial stress. Okay, so we have this as the equation. I can change the deformation in terms of formula involving stress, di ba? P over A. So this is stress L over E. This is due to axial load. This is PL over AE. Then plus the thermal. Okay? Now, if I'm interested with the stress, so I'll be removing E. I'll be removing my L. So my L can be removed. It's common in every term by dividing with L. How about this one? It can be removed by multiplying with E. So what is the result when E over L is distributed in every term? I have the first term, which is the stress needed. This is P over A. This is a stress due to axial load over the resisting area. This one, this is alpha. This is change in temperature. L over L is out, so times E. Now, if you notice, this is stress due to load, axial. And this is deformation due to a change in temperature. This is how I define the deformation due to a change in temperature or heat, no? Okay, so pwede na ko mag-substitute o value. So load 1 to 50 pound per square inch, correct? So pound per square inch na akong pag-awson on the other term. This is the coefficient which is given. So this is equivalent to, take note, times 10 to power of negative 6, 6.5. Then per inch per inch. So just don't include na lang, no? So per degrees Fahrenheit. Now, the change in temperature, nagsugod siya unsa. It started with 75 then to 0. So meaning, if 0 is the final temperature, 0 minus the initial 75, so there is a value which is negative 75, but mga dimension na ito lang na siyang ibutang og absolute. Okay? So we have 75 degrees Fahrenheit. So Fahrenheit is out. The unit for the second term will depend on the asa man gikan sa imuhang modulus of elasticity. The modulus of elasticity is also termed as the Young modulus, correct? Okay, so then calculation will follow. So there is an amount of stress developed na 18,304.17 in a unit of PSI, which can be converted also as 18.3 KSI or kilopounds per square inch. In letter B, we have another situation. At what temperature will the stress be zero? So, muna itong stress, no? Layo kayo, no? Saan pag zero sa atong stress, no? Okay, pwede siguro ma-zero atong score, pero ang stress, pangitaanan pa nag-value, saan ito pag zero? Pwede yung So, if the stress will be zero, so this is what we're going to do. Allow your temperature to compensate this amount of deformation. Now, this amount of deformation is produced when there is a load that is applied. Pero if you start with 75, try to change the temperature just to expand up to this point. Na? Expanding the member up to this point by increasing the head. So what would be the final temperature to reach this? So sa ato pa, if the deformation will take place to reach or for the body to reach this point, no? So meaning you don't need a force. So if there is no force, so sa ato pa, this stress will be equal to zero. Because as you observe also, ningon mo na, if the thermal deformation is free to take place, no? So there is no stress that is developed. So katong buhaton ini, we let our body to expand and ato lang i-limit up to this part because this is the amount of deformation that is needed, no, to compensate with the deformation out from the axial deformation. Okay, so here is the diagram. So 75 degrees Fahrenheit initially, I'm after for the final temperature so that this end will reach up to this part. By allowing this to expand due to the change in temperature, then I don't need a force to reach this. So sa ato pa, if there is no force that is needed, so meaning the member is actually free from stress. Okay? So, let us analyze. Yan naman dyan eh. Due to temperature, we have a deformation. Due to load, we have this deformation. So, these two deformation must be equal. Okay? And by formula, this is, okay, correct? So, your L, actually, may L bas mention nga value, correct? There is no value of L being mentioned because even if there's a value, your L can still be eliminated. So, removing your L will give you an equation which is kini. Or, we can just simply go with the substitution and do not include your L. No? Okay, so L is out, right? And I can substitute alpha, 6.5 times 10 to power negative 6 per degree Fahrenheit. That is the change in temperature free from L. Already, so wala na ng L. Then, P over the product of these two. So, 1 to 50 pounds, then 0.3 square inch, no? Then, 29 times 10 to power of negative 6, then pound per cent square inch. Okay? What are the units left? Pound and pound will be removed. This is also out. So, the unit left is Fahrenheit because this is a temperature, no? Change in temperature. The change in temperature can be equal to this. But what we need is the final temperature to cause a zero stress on the body. Okay. So we have atong change in temperature is final minus initial. The final is the one that is required. The initial is 75. So, the final temperature is equal to 97.104 degrees Fahrenheit. Okay, so that is how to solve, no, a problem that involved change in temperature, so stress and deformation. Basically, they are solved as that. So there will be more example, no, later, wherein we will be talking also with similar problem, no, that deals with thermal stress. Okay, so as of now, ato lang sa pudlon ko to and another example to follow on the next video. Okay, before closing, let me say hi to Engineer Jake Lanzadires. No? Good afternoon. Okay, so thank you for subscribing and watching all the time with my video. Okay, so thank you and bye-bye. No? So, for those who are interested to follow our videos, so try to subscribe and invite others also to subscribe. Thank you.